8 kilohertz. So I have that signal, and it is sampled at home. And so there is a relationship. There is really a relationship between this signal and that one. So obviously there must be a relationship between this one and that one. Right? And we need to understand that relationship. We really need to understand that relationship. And we need to understand it so that later on, maybe even this signal, we could question whether we can go back to this signal. Right? So that's the job of sampling. Because, to give you an important, if my voice now is recording on a computer, and in a computer it can only store in this original form. In this form, right? If you play a CD, the musical song is recorded in this form, this sample form. And you question whether, when you play the CD, whether it's going to give you something like this, right? Because it goes through the loudspeaker. This is what it's going to give you. So this is a very fundamental question about sampling. And we need to understand that and understand how the frequency is affected. Okay, so that is my setup. So you see that in this domain it looks like something like that. In this domain, we can maybe draw a figure, right? We start with this draw figure here. So this is the omega, and maybe we have some signal, and then I told you yesterday that it's going to be 2 pi periodic signal, right? And so we have this period, and the next time it's going to be. So when I draw them out, I just need to draw one period. Okay? So that is 8 S of omega. And this big signal here is something could potentially go forever of this capital omega of this capital omega. And as a signal processing, sometimes we would call this is a discrete frequency. As I told before, this omega telling you the frequency. Big omega, big frequency. Small omega, small frequency. And this thing here, that variable is the continuous frequency. Okay. Still okay? Still with me? Alright. So to understand this, and we know that there's connection from here to here. So when we look at this formula here, when I look at this formula here, perhaps we could write, we have xn here, xn, and we could maybe, I can write them in this form. So one simple way is I want to really try to make this two formula as close as possible. Try to make this. Because if these two things are the same, and we know this pair transformations, if they are the same, then the transform inside can be the same. Okay, now that's what I'm trying to do. So, what should we do? Perhaps now I could play around this integral with this. Okay. So that integral now, so suppose that we have this thing here, and this thing here, we know that it is equal to 1 over 2 pi integral of x omega c omega, it's sample omega e j omega n d omega, and this one goes from minus pi to pi. So now if I'm going to call this little thing here is, I want to try to get this formula here in a variable t here, because that's what I have eventually at this part here. So to do that, maybe a simple change of variable allow me to write this more conveniently. The simple change of variable is, if I'm going to do a change of variable that let capital omega equal to small omega over t with a change of variable. So this is a change of variable here. Then this allows me to write it is going to be 1 over 2 pi integral now omega now goes from minus pi over t to plus pi over t, and I have an x of s, and in here I would have omega t, and I have e to the j omega, no, capital omega. I have is omega t n omega t n and I do have here e of capital omega, and so now this thing here maybe I just have to put e omega should be t times, so maybe I have a t in front here. Okay, it's okay? Alright. So if I say that, I'm trying to, so you see that I almost have this integral, except the range integral is from minus pi over t to pi over t. Where this one is integral from minus infinity to plus infinity. So now I'm going to do a kind of, try to get some insight. How can I make the two things equal to each other? So suppose now that I'm going to suppose that my signal is omega, capital omega, going to die at least at pi over t. And it's going to be 0 from here, and then same here. Right? Because if that's the case, then this integral will be the same, because it goes from minus pi over t to pi over t. Okay, so first, so from here now, if x of capital omega equal to 0 when capital omega less than or equal, when it is bigger than pi over t. Can you still see that? Can you still see the line? Can you from that point? Okay. Suppose that is the case. Then it can really try to match these two integrals. And they are the same because x of nt here is equal to this. Right? You can put these two